Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in Electronics and Communication Engineering Department, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss a few questions related to Unit 3, that is Module 3, 8051 Microcontroller, under the course Microprocessors and Microcontrollers. Illustrate the following instructions of 8051 microcontroller with the details. First one is XCHD, DA and DI. So XCHD is exchange byte, that is exchange the lower nibbles of a byte. So if you have a data between two operands, the exchange of the digit is nothing but the lower 4 bits, that is B0 to B4, will be exchanged between these two operands, operand 1 and operand 2. So in the given example, XCHD A comma at the rate of RI. So one data we are having in the accumulator, the second one we are having in the memory location, that is internal memory location, whose address is pointed by some register where I can take from 0 to 7. So now the memory contents of the lower 4 bits will be exchanged with the accumulator content. The next instruction is a DA, which is a decimal adjust after addition. So this decimal adjust after addition will be executed after add instruction or ADC instruction, that is after addition instruction we are going to be executed, and the result should be there in accumulator. This instruction is used to convert the hexadecimal data into packed BCD number. So whatever the accumulator content is there after addition, these 8 bits, first it will check for the lower 4 bits. If the accumulator contains the lower 4 bits is greater than 9, add plus 6 to accumulator. Then examine the upper 4 bits of the accumulator. If upper 4 bits of the accumulator is greater than 9, so we are going to add plus 60 to the accumulator. So by performing these two instructions internally, the accumulator contents will be converted into unpacked BCD. The next instruction is a DIV instruction, which is a division operation. So for this division operation, the two operands, which is a dividend and a divisor, we had to place into accumulator and B register respectively. So if you see the syntax, a DIV AB, where there is no separator between A and B, we had to write as side by side A and B. So this division instruction is used to perform the division of accumulator contents with the B register. After getting the division operation, the quotient and the remainder we can see in accumulator and B register respectively. Next, explain the following instructions of 8051 microcontroller with the details. The first instruction is CJNE, which stands for compare and jump if not equal. So it is a 3 operand instruction, CJNE, operand 1 and operand 2, and where we want to jump the relative address. So here the operand 1 and operand 2 will be compared. If these two are equal, here we are checking for not equal. So if these two are equal, go for the next instruction to execute. If the operand 1 is not equivalent to operand 2, then the instruction which is at the real address, that will be executed. The next instruction is RETI. This RETI is the written from interrupt subroutine. So in an ISR interrupt subroutine, so whatever the instructions we are going to have, to indicate the end of this interrupt subroutine, we are going to write RETI as the last instruction in ISR. So whenever the processor encounter RETI instruction, the control will be transferred to the main program, where this main program I am considering is the called program, from where we got the input. The next instruction is MUL instruction. So the mul instruction is for multiplying the data between accumulator and B register. Here also the operands, that is accumulator and B register, are only allowed, and there is no separator between these two. So after multiplying the 16-bit results, we can see in accumulator and B respectively. The lower byte in accumulator and the higher byte is in B register. The next question is a differentiate between S jump, A jump, L jump instructions in 805. So in the program, whenever we have either S jump or A jump or L jump, the control will be transferred from the called program to another location. Either it may be reside in the same program or it may be upward or downward direction. So where S jump it stands for short jump, A jump stands for absolute jump, L jump stands for long jump. The difference between these three unconditional jump instruction is how much distance offset value we are going to, how much amount of memory locations we are going to have a displacement from the current instruction. So either here it can be jump in the upward or down. So if we use the S jump instruction, from the S jump instruction, the relative address will be placed with 8 bits, where it can have 120 location, 127 towards upside and 128 location in the upward side. The next one is A jump, which is absolute jump. In the absolute jump, the relative address we are going to be specify with 11 bits of address. Whereas L jump, which is a long jump, where the location we are going to jump, that we are going to have a displacement of 16 bits. So the relative address size will differentiate the S jump, A jump and L jump. 8 bits, 11 bits and 16 bits respectively. The next question is compare the functionality of move C and move X instructions of 8051 microcontroller. So this all three belongs to the data transfer instructions only, move instruction. If you have a move instruction, the data we are going to be transferred within the 8051. Either it may be a register to accumulator or B register or any memory location. Whereas MOVC corresponding to the data will be moved to the memories, and that memory is also related to code memory. So if you want to write the data to a code memory, we are going to use the instruction is MOVC. Similarly, for fetching the instructions, we use MOVC instruction. Whereas the MOVX instruction, it is for accessing the data from external memory, and this memory belongs to data memory. So the MOVX instruction is used for transferring the data from the external memory to 8051 microcontroller or 8051 microcontroller to external memory. Next, list and explain the rotate instructions of 8051 microcontroller. Total we have 4 rotate instructions, namely RL, RLC, RR, RRC. RL stands for rotate accumulator towards left side by 1 bit. RLC is rotate accumulator towards left side through carry flag. RR, it is for rotate accumulator contents towards right side by 1 bit. RRC, rotate accumulator contents towards right side through carry. In all these 4 cases, the data will be shifted by 1 bit. Either it may be left side or right side depending upon the instruction. So if you have RL instruction, this we are rotating the contents towards the left side. So the bit positions of the accumulator is assume B0 to B7. When you execute the RL instruction, the content will be shifted towards left side. So in this case, as we are considering without carry, the B7 will be placed into the carry flag, B6 will sit in MSB position, B0 will be occupied in the B1 position, whereas this LSB will be shifted with the B7. So that is RL instruction. Whereas The RLC instruction is, in RLC instruction, the accumulator contents, that is from B0 to B7, will be rotated towards left side along with the carry flag. So when we are executing this instruction, whatever B7 will be there, that is MSB of accumulator, that will be copied into carry flag, and the previous carry will be placed in the LSB position, and B0 will be copied into B1 position. Like this, B6 will occupy the MSB position. So this is about RL and RLC instructions. The next one is RR instruction, where RR instruction, it is for rotating the accumulator contents towards right without carry. Here also we will take the accumulator contents, that is from B0 to B7. We want to shift these contents towards the right side. So B0 will be placed in the carry flag, B1 will be placed in the LSB, B7 will be placed to B6 location, whereas this previous LSB, that will sit in the MSB position. This is RR instruction. The next one is RRC instruction, which is rotate right with carry. So in this, the accumulator contents will be shifted towards right side along with the carry flag. So when we shift these contents towards the right side, the B0 will be sit in carry flag, B1 will be occupy the LSB position, B7 previous MSB will be shifted in the B6 position, and the previous carry will be placed in the MSB position. So this is a rotating right with carry. Next, outline 8051 microcontroller program to convert packed BCD number available in accumulator into two ASCII numbers and save them in the internal locations 48H and 49H. So here we are given some number which is present in the accumulator. This number, which is in hexadecimal number, that we want to convert into ASCII. So for converting into ASCII, first the hexadecimal number will be converted into unpacked BCD. From this unpacked BCD, then we are going to convert into ASCII. So for this purpose, the accumulator contents, first we will retain the lower 4 bits, the upper 4 bits will be cleared. Then we are going to add 30 for it. Then the lower 4 bits is converted into ASCII. So whatever the accumulator contents are there, this we are going to have some copy in another register. Then the same contents, now we will clear the lower 4 bits and the upper contents will be retained as it is. Then we go for rotating these contents towards right side by 4 bits. Then this will be occupied into LSB position. The upper 4 bits will be have 0. Then we are going to add 30 for this. Now this is the logic for converting the given BCD number into ASCII number. So that BCD number we can have in the hexadecimal representation, that we can take as the BCD input. After converting this, we have to load into 38H location, 48H location and 49H locations respectively. So origin, which is where the program has to be stored, we will indicate with ORG 8000H. The BCD number which you want to convert, first that one will be loaded into accumulator. For this second operation, this accumulator contents will be copied into any one of the register. In this example, we are taking R2, we can take any register here. For clearing the 4 bits and logically the accumulator content with 0FH. So whenever we AND with the 0FH, so what is 0 indicates? 0, 0, 0, F indicates 1, 1, 1. So whenever we do the logical AND operation, the upper 4 bits and the lower 4 bits will be altered like this. As we are ANDing with the 0, any bit, it is going to result to 0. If we AND with the 1, it is going to retain the lower 4 bits. Next, we are going to add 30. So that we can use either add instruction, we can, or with the 30H, both are valid. So here also you can have add instruction. Next, this ASCII converted the lower 4 bits, we are going to be moved into 48 location. That is move 48H comma A. Then we have a copy in R2 that will be get back into accumulator. In this case, now the upper 4 bits we had to retain, the lower 4 bits we had to clear. So we are going to be AND with 11110000, that is F0H. So now AND accumulator contains with F0H. When you do this, the upper 4 bits will be retained and the lower 4 bits will become zeros. Now we want to convert the upper nibble into the lower nibble place. So for that, either we can go for swap the bits or we can go for rotate operation. All are valid. So swap accumulator. When you swap this accumulator, the lower 4 bits will be swapped with upper 4 bits. So that after swapping operation, here zeros will be placed, then upper 4 bits will be placed. Then add or odd with 30H for converting into ASCII number, that will be loaded into the target memory location, which one 49H. To stop the program, the last instruction is HLT we can write. Next, demonstrate using 8051 program to move an array of data between two external memory blocks. So here we have external blocks. So these two memory location, either we can take in the single block or different blocks. These two data with some address A1 and A2, we want to exchange these two data, or we want to move the data between two external memory locations, that is from A1 to A2. So the external memory directly we can't copy from one external memory to another external memory. So first we'll copy the source memory from where we were getting the data into the internal memory of 8051. Once you are copied into the internal memory, then this data will be copied into A1. From A1 to internal memory, from internal memory to A2. So here, how many number of memory locations we are going to be transferred, that we are going to be loaded into R7 register. Then what is the starting address of the external memory from where we were getting the source data, that address we are going to be loaded into DPTR. So whenever we are accessing the external memory, we are going to be load the address into DPTR. So move DPTR comma hash from address. Then this first initially it will be copied into the internal memory. So the internal memory address we are going to be load into R1. Now we will fetch the data from the external memory into accumulator, from accumulator to internal memory. That will be done with move x. Why we are using move x is because it is an external memory. So move x a comma at the rate of DPTR. From the external memory, we are going to be loaded into accumulator. Then from accumulator, we are going to be loaded into the internal memory. So for that, we use move instruction. Move x is from external data transfer. Move is for internal data transfer. So accumulator to internal memory. Next, for pointing to the next memory locations, we are going to be increment the DPTR and R1. That is external memory address and internal memory address will be incremented. So as this one, we have to continue until the number of memory locations are finished. So we will write DJNZ R7 comma loop 1. So where we have the number of memory locations, that is in R7. So for every transfer, decrement R7, if it is non-zero, go to loop 1. So this block will copy the external data from block 1 to internal memory. The task is we want to copy from external to external. So we have done till external memory to internal. Then next we go for internal memory to external memory block 2. So again we load R7 with how many memory locations we want to transfer. R1 will be loaded with the internal memory address starting. Next DPTR will be loaded to the target location, that is from where to where we want to copy, that the two address is going to be loaded into DPTR. Next, first internal data will be copied into accumulator by using the instruction move a comma at rate of R1. Now this accumulator contents will be copied into the external memory by using move x at rate of DPTR comma a. So for pointing to the next memory location, increment the external memory address which is in DPTR and internal memory which is in R1 register. So as these are a continuous process, so where we have the count in R7 for every memory transaction, a decrement R7, if it is non-zero, go for loop 2. So DJNZ stands for decrement and jump if not 0. Then halt, which is for stop the end of the program. Show the use of push instruction to put the numbers 82H in RAM location from 34H to 37 location. Also list out the same program without using push instruction. So here we will write the program by copying the data by using push instruction and without push instruction. We will assume the stack pointer is addressing to the memory location 33H, origin 8000, which is the starting of the program. Then stack pointer will be loaded with the move instruction sp comma hash 33H. So the data whichever we want to copy into this memory location, that is 82H, first we will load into either register or memory location. Here we are taking 50H location. Here from 34 to 37, that is 34, 35, 36, 37, 4 memory locations we are going to copy. So that number of memory locations we are going to be loaded into R7. Then whatever the data which is present in the 50H location that we want to place onto the top of the stack. So for that we use the instruction push 50H. Now 50H memory location contents will be placed into the top of the stack. Then as one data transaction is done, we will decrement the count, and if it is non-zero, go to loop 1. So these two instructions will be repeated for 4 times for loading the data from 34H to 37 location. Then we will stop the program by using HLT instruction. So this is by using push instruction. Next we will see without push instruction how many memory locations we want to copy that will be loaded into R7 by move R7 comma hash 04H. Then the starting address will be loaded into one register that we are taking as R1 with the move R1 comma hash 34H. So the data which you want to copy into that memory location, that is 82H, will be copied into the memory by using move at the rate of R1 comma hash 82H. So for addressing for the next memory location, go for incrementing the address which is there in R1. As one data is transferred, decrement R7. If it is non-zero, go to loop 1. So this loop will be repeated until the count which was placed in R7. Once all the data is transferred, we will stop the program by using HLT instruction. Next, demonstrate the program in 8051 to count the number of 0 bits available in a byte in the external memory 1000H. Store bit count in the internal RAM location 60H. So here we have the data which is at 1000H, which is external memory. What are the contents we are having here, that is B0 to B7, we need to find out how many zeros are there. So for this, we will shift these contents either towards left side or right side by 1 bit. Then we will check whether the carry flag is equivalent to 0 or carry flag is equivalent to 1. If carry flag is equivalent to 0, it indicates the bits in that given data are having 0. So we are going to be increment the count. If carry flag is equivalent to 1, don't alter the increment. So here we go for incrementing the register. Here no operation will be done. We go for next bit check. Now we will see the program. So move R7 comma 08H because we want to check the 8 bits. So that 8 we are going to be loaded into R7. Now we want to fetch the data from the external memory. So the external memory address first will be loaded into DPTR. Then move X A comma DPTR. So from external memory the data will be copied into accumulator. Next move R0 comma hash 60H. This is where we want to store the data after counting. Move at the rate of R0 comma hash 0. So this count initially initialized to 0, the memory location contents. Next, we will rotate these contents towards left side by 1 bit, B0 bit. Then it will be moved into carry flag. Then we'll check for carry flag. If carry flag is equivalent to 1, what indicates the bit is non-zero. So don't go for incrementing, just skip the data. Increment. If carry flag is equivalent to 0, then we have to go for incrementing the 60th memory location, which is there in the R0 register. So increment at the rate of R0, the count will be incremented. So this we have to repeat for 8 number of times. For every bit check, decrement R7. If it is non-zero, go to loop 2. Next we will see, illustrate how to find the average of 5 8-bit number, and the result we have to store in 55H in the microcontroller. So here we have the 5 8-bit numbers. So this data num1 to num5, we are going to add all this for generating the sum. Then we will divide this one with 5 for getting the average number. Here, move r0 comma hash 30, the address of the starting memory location of n1, we are going to be loaded into r1. How many data we are going to check? 5 data, so the count will be places in r1. The initial sum will initialize into r2 register as 0. Accumulator contents is cleared. This also instruction we can exclude. Move a comma at rate of r0. So this n1 data which is at 30h will be loaded into accumulator. This data we are going to add to the initial sum which is in r2 by using the instruction add a comma r2. Then the sum which is there in the r2 again will be fed back to r2 again. For pointing to the next address, increment r0. As one data we are added, decrement which is there in the count in r1 register. If it is non-zero, go to loop. So this loop will be iterated for 5 times. Once it is done, we are going to be load the 5 value into B register, because for division instruction, the syntax is a comma p, where B is the divisor. So the divisor here in this case is 5. What about A is? A is a dividend. Dividend is nothing but sum which is there in the R0 register. So R0 register contents will be loaded back into accumulator. R2. The result is in R2 register. So R2 register contents will be stored into accumulator. So for that, move A comma R2. The result we have to store into the 55 location. So move R4 comma hash 55h. Then we go for divide A comma B. This is the instruction for division of A by B. Then the quotient will be there in accumulator, that will be loaded into the target location, that is 55h. Here if you want to consider the remainder also, then we are going to be load into move. Before that we will increment R4, that is address. Then we'll write move R4 comma B register, because A will contain the quotient and B will have remainder. Then we will terminate the program by using HLT instruction. If the number is producing remainder is 0, then these two instructions are not required. Next, show the ALP for smallest number in a given array using 8051 microcontroller. So for finding out the smallest number, if you have a series of numbers n1, n2, n3, n4, first we will check n1 is compared with n2. If n1 is greater than n2, the smallest is n2. So this will be considered. Again, n2 will be compared with n3. Assume n2 is the smallest number. As this condition is fails, so we will take the n2 number. Then we will compare n2 with n4. After comparison, which are the smallest, that we are going to be filled as output. This is the logic for finding out the smallest number in the array. Next, write a program to compute the sum of n numbers and save the sum into 70h. So here we have the number of entities are 15. We are going to be load the initial sum as R0. We will clear accumulator. So as we want to count from 1 plus 2 plus 3 plus 4 like this until n. So first we are going to be increment R0, because 1 we are going to add. Then add a comma R0. R0 we have to consider until n points. So we'll compare R0 with n. If these two are not equal, go for next iteration, because we want to add 1 plus 2 plus 3 plus until n. So increment R0, then it will be go to 2. This will be added to sum. Now we'll get 1 plus 2 in the accumulator. Then it will compare with R0 with n. As 2 is not equivalent to n, again it will be go to loop. So this addition operation will be takes place until n number of additions. Once the addition is done, the result which is in accumulator, that will be moved into 70h location. Next, describe the register set of 8051 microcontroller with example. So here we can see this is the architecture of 8051 microcontroller. The register bank, we can have four register bank in the internal memory, that is bank 0, bank 1, bank 2, bank 3, where each register bank is consist of R0 to R7, which is in register bank 0 as well as bank 1, bank 2 and bank R0 to R7, R0 to R7, R0 to R7. Apart from that, we have some special function registers like IE. IE stands for interrupt enable, IP register, interrupt priority, PCON, power control register, SBUF, serial buffer, SCON, serial controller, TCON, timer controller register, TMOD, timer mode register, TL0, TH0. These are registers for timer 0, for timer 1, TL1 and TH. These are the various registers we are having in 8051. Apart from that, we can have register A, which is accumulator, B register, program counter, which will store the next instruction to be executed, and a DPTR, which will hold the external memory address. Explain the internal architecture of 8051 microcontroller in detail with the diagram. So the figure shows the architecture of 8051 microcontroller, where we can see the four ports, that is port 0, port 1, port 2 and port 3. Then the register bank set, which is a part of internal memory and SFRs. Next we have internal RAM, which is a 4K. These SFRs are nothing but the internal memory elements. PSW, program status word. ALU, which will perform arithmetic and logical units. The inputs are provided from accumulator and B register depending upon the instruction. Then program counter, which is going to hold the address of the next instruction. DPTR, for accessing the external memory, the address will be loaded into DPTR, where DPTR is a 16-bit, which we can program like a DPL as well as DPH register. Next, this system time, system interrupt and data buffer memory control, we have a control. These are the various blocks of internal architecture of 8051. We have to elaborate a little bit on this. Outline the addressing modes of 8051 with examples. So addressing mode is how the data is presented. So in 8051 microcontroller, there are various addressing modes like immediate addressing mode, direct addressing mode, register addressing mode, register indirect addressing mode, indexed addressing mode, and implied addressing mode. So immediate addressing mode means the data should be present in the instruction itself. So the immediate data always it will be preceded with a hash symbol. Direct addressing mode means the data is present in the memory, that memory address directly we are going to be placed in the instruction like 40H. Register addressing mode. Here the content is in register that we are pointing to by means of any one of the register. Register indirect addressing mode. So here the data is present in the memory, that memory address we are going to be loaded in any one of the register. So where @ will be indicates the memory, where the address is here we are having this example is R0. Index addressing mode. So in this index addressing mode mainly used for getting the code from the code memory, where the address will be loaded with the program counter with the offset value in the accumulator. The addition of accumulator contents with the PC will use the target location, that contents will be loaded into accumulator. This is for reading the instructions. Next, implied addressing mode. So if you observe RLA, where explicitly we are not specified the operands. So by default, the implicit operand is accumulator. Next, explain the significance of bit addressable feature in 8051 microcontroller. Show the various components of internal memory. So internal memory, we are going to have the addresses from 00 to 7F, which is 128 memory location, out of which we have 8 registers in bank 0, 8 registers in bank 1, 8 registers in bank 2, 8 registers in bank 3. After that, we have a bit addressable area from 20 to 2F, where 16 memory locations we are having, where we can access the data byte-wise as well as bit-wise. So whereas the remaining addresses, that is from 0 to 1F, from 30 to 3F, we have to access the data like byte-wise. This is byte addressable. This is also byte addressable. Whereas this blue portion, we can go for bit addressable as well as byte addressable. So if I want to change this, only I can go for a set that particular bit. I can write a set B, the address is 30. So 03H is this memory location. Only this bit will be altered. So this is about the bit addressable feature. Next, elaborate the significance of the following signals of 8051 microcontroller. The first one is PSEN bar. So whenever we want to load the code into the code memory, this pin we have to connect to ground. Once the code is loaded into the RAM, this PSEN bar usually be connected to VCC, so that write operation will not be performed for RAM. Next, XTAL1, XTAL2. So between XTAL1 and XTAL2, we are going to connect a crystal oscillator where the required clock pulses will be generated to the microcontroller between these two pins. Next one is T0, T1, which are timer interrupts for timer 0 and timer 1. Describe the features of special function registers of 8051 microcontroller. So there are various SFRs existing in 8051 microcontroller like accumulator, B register, program counter, DPTR, where DPTR will have two 8-bit registers DPL and DPH, stack pointer, program status word, port 0, port 1, port 2, and these are the addresses of the corresponding registers. Whichever the register which you are having a star, they are bit addressable. If you don't have any star, this is byte addressable. Few more SFRs we are having. For timer 0, for placing the count, TL0, TH0, timer lower byte and higher byte. Similarly for timer 1, TL1 and TH1. For using the timers, we have two SFRs corresponding, timer control and timer mode. For serial communication, 3 registers we are having, SBUF serial buffer, SCON serial port control, PCON power mode control. For interrupt, we have 2 registers. One is enable the interrupts using IE register, whereas giving the priority through IP registers. These are the addresses for the corresponding registers. Here also the star indicate bit addressable. If star is not present, it is byte addressable. So bit addressable registers, either we can go for bit addressable as well as byte addressable. Show the PSW, that is program status word register format in 8051, and give example instructions which will affect the respective flags. The first one is parity flag. So where this parity flag will use the number of ones in your data. Then overflow flag. So for every instruction, this parity flag will be affected. Overflow flag, whenever the target size and result size is differs, then we are going to get overflow flag. This RS1, RS0, this is for selecting register banks. Whenever these two are 0, 0, register bank 0 will be selected. 0, 1, register bank 1 will be selected. 1, 0, register bank 2 will be selected. 1, 1, register bank 3 will be selected. This is not defined. This is for user defined cases. We can take this flag, but no significance is there. Auxiliary carry. So whenever there is a carry generated or borrow is taken at lower nibble of the data, then we are going to have auxiliary carry. The carry flag, if there is any borrow is taken or any carry generated in the MSB position, then we are going to have the carry flag. So this is the program status word in 8051 microcontroller. Outline ALP to find out even and odd numbers in a given array of 8051 microcontroller. So for finding out whether it is a given number is even or odd, just we are going to check the LSB bit. If LSB bit is equal to 0, we will decide this one as a even number. If it is 1, odd number. So once if you are defined that one as a odd number, we are going to be load the accumulator content as 0, 1H for odd case. If it is even, accumulator will be loaded with 0, 0. So first we are going to be move accumulator content, accumulator with a given number. These contents we are going to be shipped towards the right side, either without carry or with carry. Both are valid. Towards right side by one time. Then we'll check for carry flag. If carry is 1, we are going to odd label. Where odd label, we are going to be load with 0, 1. If carry is equivalent to 0, that indicates it is even number. So we are going to be load accumulator with the 0, 0. Just we will jump to even where nothing is done. Because our objective is we have to load into 0, 1 for odd number, 0, 0 for even. So thank you. So in this session, we have discussed the question bank related to module 2, which is 8051 microcontroller. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.